All right, everyone. I know that may not have been enough time, but it is due tomorrow at 3 o'clock. I just sent the email to you. So just work it out and send that to me tomorrow. And I'm going to count that as a quiz grade. I hope getting together in groups helped a little bit as far as kind of knowing what you're supposed to do. Yeah, any questions?
At the end of the class, could you maybe just leave the session open? We can go back into the group.
Yeah, I mean, that's fine. Okay, all right, so today, what we learned last time is, that there are two definitions of the derivative, right? We now know that there are two, and that the one with h going to 0, f of a plus h minus f of a all over h, that's kind of the main one. And then we also talked a little bit at the end of class how the derivative represents the instantaneous rate of change of a function at some point. And so depending on the function, I told you if you have like distance versus time, something like that, then it gives you your instantaneous speed or velocity. It could be force versus time, and then it would mean something else. So it all depends on the actual function and what kind of universe it lives in. Is it a physics problem? Is it a engineering problem? But the key is we can find the instantaneous rate of change of any function at any point, so long as we can evaluate the limit. I mean, now the algebra, as we have seen, can get kind of messy. So the reason I wanted to start with this problem was because I wanted to show you what the graph of this was, the graph of this function. So here is the function. Did I close it out? Oh no, here it is. Close this one out. Okay, so here's the actual graph of that function, all right? So the graph goes up, and then it goes down, and it goes back up, right? That's the graph of x cubed minus 3x squared plus 6. So if I were to go to some arbitrary point on this graph, let's just say here at 1, right? And I go up to the graph like this, then I have a point there. The derivative, right, f prime at that point 1 is going to be equal to a number, isn't it? Now, the derivative at a is going to give you a function with a in it, right? In other words, the answer you get is going to be some expression that has a in it. So once you figure out this general derivative, then you can just start plugging values into it and get a number as an output. Agreed? Now, in this picture, would that number be positive, negative, or 0?
That should be negative.
Why?
Because it's sloping downward, so it would be a negative slope.
Yeah, the tangent line here, that's a terrible tangent line. Why is that not erasing? There we go. The tangent line here, the slope of it, which is what the derivative is at that point, is the slope is negative, right? So I would know not only is this a number, I would know that it's a negative number, right? And if you look at any point that I pick for x down here, anywhere between here and here, between 0 and 2, do you agree that if I go up anywhere here, I'm going to get a derivative that's negative?
Yeah.
Because anywhere there, the graph is going down. Now, the graph is green and red and then green again. Do you see why I made it green, then red, then green?
Because the green is going to be positive?
Yeah, the green is representing where the slope of the tangent line would be positive. The red is signifying where on the graph that the slope of the tangent line would be negative, right? Does that make sense?
A question.
Yes.
How do we? Why is it that it's going down? Because from left side it can be, and it can go up.
Well, I'm only referring to this section right here.
Yeah.
So when we read a graph, and we talk about it's going up or going down, we're always reading it like we read a book from left to right.
Oh, okay.
Yeah, because if you go from right to left, then you could say it's going up, right? But we're
Mhm.
always going to be reading it as we move from left to right.
Okay, got it.
Okay, so we're going down here, right? Down, 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 down. All right, so if I pick any value of x between 0 and 2, the derivative is negative. We're all good with that? If I pick any value between, let's say, from 2 on forever, or from 0 this way, right? Then my derivative would be positive. Now that's important because the next connection I'm going to try and make with you is, it's one of those things where students struggle with it until the light bulb goes off, okay? And sometimes it takes a while for the light bulb to go off for students. This idea now we want to extend, and that's going to bring us into the next section, all right? This whole idea of how the up and down of a function somehow is dictated by the value of the derivative. If the derivative is negative, we know the function's going down. If the derivative is positive, we know the function's going up. And what if the derivative is 0?
Then it's flat.
It's probably flat, right?
Yeah,
You just got
like
line then.
you'd have a derivative of 0 at 0 and at 2, right?
It looks like here, right up here at this point, and right here, we would have slopes that would be 0, right? Okay, so let's get into today's stuff. All right, let me get to my lecture notes, and then we'll get back to this picture. Okay. All right, so 2.2. We're moving at 2.1. We're into 2.2 now. The derivative as a function. All right, so the quiz problem I just gave you, your answer is going to have a bunch of stuff with A's in it, right? And when we finished class last time, the examples that we did at the end, right? Remember this problem? I said, hey, take this function, find the derivative at A. The algebra was just a mess, but look at our final answer. Our final answer, you could look at it as being a function of A, right? It's some function of A. This would be the derivative, okay? But at the end of the day, remember what a function is. A function is something that takes something in and spits something out, right? So if I plug some value of A into this, it's going to spit an answer out. Just like this right here is a function, right? This is a different function, but if I plug in an X, it'll spit out a number, right? Plug in X, goes through the function, spits out some number that corresponds to that X. That's the idea of a function. The derivative can be looked at as a function. It is a new function though, right? Like this is the original function and the derivative is a new function. With me? Start with F. The derivative is a new function, right? So that's what 2.2 is about. It's about trying to somehow make a connection now that the derivative at some value, right? I'm sorry, the derivative here gives us some new function, right? But we used A, didn't we? We said, okay, let's start with some graph. Let's pick a point A, and then we'll do another point to the side of it, A plus H. And then we slid that point over here, right? And that's when we let H go to 0 to do that. We did this last class, right? This look familiar? But I used A, right? Could I have used B? Could I have used
Yeah.
C?
Could
Right?
have used any
used
number.
Any letter I want, right?
Letter.
Right? I could have used A, B, C. So why not just use X? Why not, instead of doing this, call this X? That's X plus H. If we do that, then our answer, right? The derivative here, the derivative at X, the only difference in the formula is that instead of using A, we use X here and X here, right? So, I mean, we're not really doing anything different other than using a different letter. But it's a little more profound than that, because what it means is that we start with a function. Again, I'm going to keep repeating myself today with this. We're starting with a function f, right? We start with a function f, right? That's what we start with. Then we do something to it. We take the derivative of it. Now, when we do that, that requires us doing the limit, blah, 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 right? That limit. But what we get out is a new function. And that new function is f prime of x, or we were saying a, now we're going to start saying x. So guess what? If our original function was a function, we could graph it on Desmos, couldn't we? Well, if the derivative is a function, can't we graph it also? We should be able to, right?
Yeah.
We should be able to graph the function, the function and its derivative. And somehow when we look at the two, there's going to be something, some relationship between them. And we need, that's our goal right now in this class right here today, is that you need to see the relationship between the graph of a function and its derivative. They have this intimate connection, but it's a little bit hard to see for some people. So let's see if I can help you see it. All right, here we go. So here is a function, all right? Here's a function f. As I move across this function with a point, right? If I move across this function with a point, can y'all see that okay? We'll make this a little bigger, make it bigger. So as I move across this function with a point, just imagine that that point corresponds to, you know, us picking some x value, and there's our point, right? If I go now and I ask you, what is the derivative of that function at that point, at that specific point, x? It's going to, this answer right here will be a number, won't it? And it's going to spit out the slope of that tangent line. And it will be negative here, won't it? If I move that point somewhere else, like over here, right there, will I still have a negative answer?
Yeah.
Yes, but is it as negative? Do you know what I mean by as negative? Like this little tangent line right here is pretty steep, isn't it? But the one back here is still negative, but it's not quite as steep.
So it'll be a smaller number.
So it'd be a smaller negative number, right? A smaller negative number. And if I go even closer to here, like there, will I still have a negative slope?
Yes.
Right? But it still will not be as big. It'll be a small negative number. So the more steep you get, the bigger your negative number gets. The more shallow the pitch of the line is, the smaller the negative number is. And then if I go to this side, let me go over here, there I'm going to have a positive number, right? The derivative will be positive. And if I move, let's say this way, I'll still be positive, but not as big, right? Okay, so let me see if I can animate this and make more sense to you. I'm going to move my point over here. Okay, I'm going to start it right here. And what I'm going to do is I'm going to have the computer go ahead and for this point, it's going to calculate the derivative. It's going to find the value of the derivative and it's going to plot it on the plot it right. Well, let me just put it here. Here we go. Here's the tangent line. Okay. The computer just is showing me the tangent line, the slope, the little tangent line here, and it's plotting. I mean, so not plotting, it's giving me the value. So do y'all see that that's a small negative number there? Okay, so the input here, the input, I can't tell what the input is, negative 1.46. So what's happening here is we are plugging negative 1.46 into the derivative, and it is spitting out negative 0.61. So this is the x, and this is the derivative. Understand? Plug in negative 1.46, come down here, measure the slope of that tangent line. It's negative 0.61. I said 0.61. So this is a point, right? I mean, I could look at that as an x and a y coordinate. So I'm actually going to now have the computer plot that point for me. There it is. See? That point is plotted right there. You go to the left and down 0.61. Now, as I move to the right, let's see what happens to that point. I moved too fast. See it starting, see what's happening here? We get to about right. I can't quite get there. Right there, there we go. You see how when I get here, the slope looks, well, it's almost zero. Do you see that my point here is almost at zero? When I say zero, up and down zero, right? If I keep moving to the right, Now it's positive. So the point goes up above the x-axis. Really big positive number. Now it's going to be a smaller positive number. And then it's coming back to 0. Boom. Now it's going to go negative because my pitch of my line is negative. It's going to get really big negative. And then it's going to start coming back, still negative, right? Still below the x-axis. And then when I get to here, the slope of the tangent line is about 0. You follow that? So now let me put it all together. If I plot these points and leave them there, here's what I get. That is the graph of the derivative. All right, so let's see if you can wrap your heads around this. Everywhere that, look at the red graph, right? Look at the red graph. Everywhere that you see, let me see what color I want to use here. Do I have green? I do have green. Okay. Everywhere on the red graph that we're going, let me look at everywhere we're going up. So from here all the way to here, would you all agree that we are going up? We're increasing there. That means that the slope of the tangent lines must always be positive there, right? So notice that in this region, from here to here, in this region, do you see that the graph of the derivative is positive, meaning it's above the x-axis? It's a positive, it's spitting out positive values. Then when I move to the other side, when it start coming down here, now my graph's coming down until I get right there to the bottom. So the original function here in this little window, right? In here, the graph is going down, which means the derivative should be negative, right? And you can see that the graph of the derivative is in fact negative below the x-axis. And then you go on to the other side and it's positive, right? It starts, the graph starts to go up right over here. Where's my cursor? Right over here, the graph starts to go up. So you can see that the derivative would be, again, positive. Okay, just, I know not everyone has their camera on, but just a real quick show of hands that you're making this connection, yay or nay? Show yes or no. It's okay if you're not. Okay, so we're gonna do another one because you gotta really kind of make sure you understand this before you can move on here. All right, so there's a graph of the derivative. Questions?
I had a quick question about,
Yes.
sir. I had a quick question about these two functions right here. So whenever so the derivative and then the regular function, whenever we see it intersect, whenever it intersects, does that mean that every time it touches it's 0?
No, good question.
No?
Where they hit each other is irrelevant.
Okay.
It's irrelevant. In fact, on the next example, the one that I showed you at the beginning of class, this one, I intentionally made it here. I'll graph the derivative for you just so you can see it. There's the derivative of that one. And they don't, where they hit each other is a completely arbitrary point. Like it doesn't have any significant meaning here.
Got you.
Okay.
So basically the takeaway from this is that of f of x, if the slope is positive, the derivative is going to be positive. The slope is negative, derivative is going to be negative.
Yeah, if the slope is positive, so the original function, if the slope is positive, then our derivative will be positive, which means its graph will live above the x-axis. If
And
the
our
original function slope is negative, that means the derivative will be negative, which means its graph will lie below the x-axis. Hunter?
at any point where our original function has a slope of 0, our derivative function will have an x-intercept.
Exactly. Anywhere where, so go back to this one, where, look at the red graph. At what points do we have the graph have a slope of 0? So you can see here, it has a flat tangent line. Here it has a flat tangent line. And down here it has a flat tangent line. And if you go and look at the derivative there, this is what Hunter is saying, you'll notice that the derivative has an x-intercept there. And here it's right on top. Here, the derivative has an x-intercept. Let's look at another one. So take a second to analyze that for a moment. There's the original function. it's always increasing, isn't it? It's always going up. Not only is it always going up, it's always going up at the same rate, isn't it? Like if you pick any point you want here, the slope of the tangent line is actually equal to the slope of the line, isn't it? The slope of the tangent line would be slope of the line.
Yeah. So may I take a guess as to what our graph of our
Sure.
derivative would look like? Would it
Sure.
just be a flat line horizontal to the x-axis?
It'll be a flat line because the derivative here at any point is constant. You could almost look at it like the rate of change of this function, right? The rate of change of this function is constant. And so the derivative must be constant. So I'm going to do the same thing. I'm going to move across the function here. There's the slope. You see my little green little slope? Notice that it's calculating the slope to be 3. No matter where I go, the slope is 3. So if I go and graph this, right, it's going to just be the constant 3 function. So do y'all see that where the original graph hits the x-axis has nothing to do with the derivative here? Like there's nothing to do with it. It's all about the slope of the function. It's all about the pitch, the up and down, the increase, decrease. Let me just say it one more time. On this function, the derivative is always positive. So we should expect that the function, when we graph the derivative, it should always be above the x-axis, which it is. But further than that, or more than that, the slope of the tangent line at all these points is the same. So not only should the graph of the derivative be above the x-axis, it should always be the same value, which is why it's constant. Yeah? Okay.
That's
I
baller.
have a question.
Mhm.
Is it positive because the red line is going up?
Yes. From left to right. From left to right. Right. Okay, so I have one for you here. We're going to get back to this one. I have another one I wanted you to look at. Okay. Let me zoom out of this a little bit. There we go. Now I've kind of cheated already because I've done part of the graph green and red and green. But I need to first tell you this right here that you're looking at. This is the graph of f of x, okay? I would like to see if we can graph the derivative. Can we graph the derivative? Okay, so let's start by moving from left to right. As we move from left to right, we're going up, 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 right? So I should expect that my derivative lives where?
Above the x-axis.
Above the x-axis, okay.
Positive.
But more than that, it's a straight line, right? So that means that the slope of the tangent line is always constant. Can you tell what the slope of this green line is?
1.
1. You can tell by rise over run, right? If you pick a point, just pick a point and just to get to the next point, you go up, over, right? Can y'all tell it's 1, rise over run?
Yes.
Maybe just go here. If you go up here, you'll have to go up 6 and over 6, right? Up 6 over 6. So 6 over 6 would be 1. So the slope of this line is 1, which means the derivative should always be what?
1.
Positive 1.
1, positive 1, right? So I'm going to graph that, right? Here comes the derivative. And that's only when I'm on this side of 0, right? From 0 to the left, my derivative should be 1. So 1 is about right here. So my derivative should go like this. Make sense? Now between 0 and 2, right, my original function is going down from left to right. So I should expect that the derivative is what?
Gonna dip below the x-axis.
It'll be below the x-axis, right? Negative. Now, will it always be the same value?
Yes. Looks like
Yes.
it.
Because it's
Yes.
a line, right? It's a line. So we should expect that I'm going to get a negative out for the derivative, and it should always be whatever the slope of this line is. So can you tell what the slope of this is?
Looks like
-2.
-2.
Yeah, we go from here to here. You have to go down. Let's see, that's down 4 over 2. So
Yep.
negative 4
Negative
over 2. So negative 2. Yeah.
Mhm.
Okay, so here's my derivative down here. That's what the graph looks like of the derivative. And now from 2 on to the right forever, it appears, I'm going to start going up again, which means my derivative when I graph it will be above the x-axis. And that's always constant slope, right? Because it's a straight line again. So I just need to know the slope of it. So it looks like I
Like
go
3.
from 2, yeah, up to 8. 2 up to 8, that's 6, and then over 2, so 6 over 2 is 3. Looks like a slope of 3.
Looks
So
like
that means I'm going to go, starting at 2, I'm going to go up to 3. 3's here. And I'm going to draw to the right like this. There we go. What you see in red, pink, whatever you want to call that, magenta, I don't care. That's the derivative of that function. So
question.
now an interesting question. Hunter, hold on.
Okay.
Now an interesting question. This might be what you're about to ask me. Can anybody think about or just consider what is the derivative of this function at 0? So go to 0, look at your function. What is the slope of the tangent line there?
0.
Kind of looks like it's 0 again. It's going to be that that cross.
Yeah. Wouldn't that be a point at 0?
Well, look at your derivative, right? Look at this derivative. This is the derivative, right? I'm asking you to tell me what is the value of this function we just drew at 0? Well, look to the left of the 0. To the left of 0, what is it?
It's approaching 1.
1, right? And to the right of 0, what is it?
Negative 2.
Negative 2. So what is it at 0? Well, I don't know.
Undefined?
What is it, right? Well, remember the derivative is a limit, right? The derivative is a limit. At the end of the day, derivative is a limit. And for a limit to exist, it must exist from both sides, right? Does the limit exist from both sides of this thing?
No.
No, because it's come from 2 different
2
places.
different values. Exactly.
Oh.
So this limit, this right here, this derivative does not exist. And what will tip you off to that, the reason you know that is, do you see how it's a sharp corner? See how that's a sharp corner right there, like a point? Anytime you have a point on a graph like that, we call them corners. If you have a corner on a graph, the derivative cannot exist at that corner. It's kind of like, the way I like to think about it is, imagine you're the derivative, right? You're the derivative, okay? So as you're moving on this function from left to right, you're the value, you take on the value 1, right? That's what you are. You're the number 1. You're the number 1. You're moving along. You're the derivative, right? You're 1, 1, 1, 1, 1, 1, 1. And then you get to this point, and as soon as you step to the other side, what are you?
Negative 2.
Negative 2. That rapid change from 1 to negative 2 with like no smooth transition. It's not like you were 1 and then you were 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3. You didn't slowly start to switch over to negative 2. It was this abrupt change from 1 to negative 2. And that abrupt change basically kills you. Okay. It has to be smooth transition. It can't be an abrupt change. So in the case that you have an abrupt change like that, you have it does not exist. Now, is that the only place where the derivative would not exist on this graph?
It wouldn't exist on 2 either.
Yeah, 2.
At
Yeah,
2.
it wouldn't exist at 2.
At 2 also, you have another corner there. So the derivative here at 2, we would say does not exist.
This is kind of embarrassing, but how did you get 3 for that slope on the right over there?
I just took 2 points here and here, and I asked myself, how much do I have to go up to get from here to here? That's rise. So I went from 2 to 8. So I rose up 6, and then I went over from 2 to 4. So I went over 2. So rise over run. Don't feel bad about asking those questions. I promise you, you're not the only one. You're just the only one brave enough to ask. So good. Okay, I hope this is starting to sink in a little bit. Let's go to the function that we started class with. Here's the graph. Okay. This is different. What's different about this compared to the previous one? What makes this one harder?
It doesn't go like
It's not constant.
Yeah.
It's not a constant derivative, right? When you have little jagged line segments, then you know that on each line segment, the slope is always the same, right? So then when you draw the derivative, it's just a straight line. Here we don't have that, right? I think we can all agree that to the left of 0, hopefully you agree with this, that to the left of 0, if we're looking this way, right? As we move from left to right, I think everyone would agree that the derivative there is positive, right?
Yeah.
Which means when I graph it, it should be above the x-axis. But it's not constant, right? It's not constant. And between 0 and 2, right, the derivative is negative. So we know it's below the x-axis. But again, it's not constant. It varies. It varies. It's steeper in some spots than it is in others. And then to the right of 2, I hope we would all agree that the derivative is positive. But again, it varies. Does that make sense? So the key to this one, I think the key is to start at the places you know for sure. Here and here, what can you tell me about the slopes of those tangent lines?
They're going to be 0.
Those are 0, and we don't have a corner there, right? We don't have a corner. So if you can imagine moving along the curve, if you're taking these tangent lines as you're moving, do you see how they slowly like roll over the hill? They didn't have that up and then boom, quick flip, right? It was a slow roll over the hill. So at the top, you get to the peak of the hill there and your slope of your tangent line is 0. So I can plot that point, can't I? I can plot my derivative. What is the value of the derivative here?
It's at 0.
0. So that we said is like an x-intercept on the derivative. And then this one right here, right? I know that the value of the derivative is 0 also. So it's not above the x-axis, not below the x-axis, it's on the x-axis. So those 2 points I know live on the derivative, right? Let's try the middle section first. Where in this middle section do you think you have the steepest negative number, like the biggest negative number, the steepest value?
Right in the middle.
Like in the center.
Looks like in the middle, right? Like right here, looks like the steepest you're ever going to be. Now, we can't say exactly how steep it is, but what we can say is that it's a negative number, right? So at this x value, the derivative should have a negative number and it should be pretty big. I'm just going to guess. It's going to be about right there. If I pick any point to the left of that, would you agree that I would still have a negative number, but not as big? Not as big as this one.
Yeah.
So maybe if I pick this one, I come down here, maybe it's there. And if I keep moving this way, I'm going to have still negative numbers, but they're getting less steep, right? Which means they're getting smaller. So I just keep on having numbers like this. And then you could make the same argument on this side that you still have negative numbers, but they're becoming less steep. So they're becoming smaller. And so what you get is something that looks like this. Questions? Tell me about the derivative at 3, right about here.
It's getting steeper, but it's not like the steepest point yet.
Okay, so
it
it's
is a
positive,
positive
right?
number.
It's
Yeah.
a positive number.
gonna
My
be above
derivative
the
is positive
x-axis.
here, right? So I'm just going to put a positive number. I'm just going to put, I don't know. I'll just put a positive number. There you go. And then as we move to the right and pick another number over here, like maybe here, and we look at the steepness there, that's even steeper, right? Positive.
Yeah.
So that means I need a bigger positive number. And then the further we go to the right, the steeper it gets, right? And steeper means that my derivative gets bigger and bigger on the, or, you know, further up above the x-axis. So it looks like this. And so if we connect these together, my derivative should look like that over there. What about right here? If I take this value, come up to my derivative, come up to my function and look at the slope of the tangent line there, it's positive, right?
Mhm.
But it's not very steep because I'm starting to round that corner. So it's going to be a positive number, not very big. If I go over here further to the left, I have a very steep slope, right? And it's positive, which means I'm going to get a bigger positive value out. So it's going to be like up here. And the further I go to the left, the bigger those positive values get. And so if I put that together, I get this. So that is the rough sketch of the derivative. Now, did anybody get the answer to the quiz? Don't tell me what it was, but did anyone get the answer? Was it a
Yes.
quadratic?
Yes.
Should have been
I
quadratic.
think we got it, yeah.
It was quadratic. Look at the picture we just drew. It's a parabola, right? And as we're going to see next week, if you start with a third degree polynomial, anything with x cubed in it, when you take the derivative, you'll always have a parabola. If you start with a parabola and take the derivative, you'll always have a linear function. So what happens is when you take the derivative of polynomials, the power comes down. The derivative is always one power less than what you started with. You'll see later. Now, before class, I actually did this and I had the computer do it precisely. Here's the actual derivative graphed correctly.
Does,
So,
sorry, what?
oh, I was just gonna say, so does that explain that other method that you showed us and told us not to use?
Yeah, the one where you that little
we
shortcut
like-
method, where because remember it
Yeah.
the exponent like automatically went down. So the next one.
Yeah, I said you will be able to use it. We can't use that yet.
Yeah, not yet, yeah.
Yeah.
Like, we're gonna use it later, but yeah.
But that
Oh,
right there,
that makes sense. Oh,
yeah, that kind of is, now if you think about that, if I told you to bring the power down, right? And then subtract one from the power, that just goes to reinforce what I just said, that if you start with a degree n polynomial, your derivative will always be n minus 1. It'll always be 1 less than that degree. Okay, we good? We good? I mean, the book, what it does in the first few problems is it gives you a bunch of graphs, and then it gives you a bunch of graphs of derivatives, and you're supposed to match what graph goes with what derivative. It's actually a pretty cool exercise because it really kind of tests, are you able to make these connections? Okay, now we move on. And this is where we have to like pump the brakes for a minute. Okay, we have to pump the brakes. And we're about to start to get into the shortcuts, okay, which is where we don't have to do the limit anymore to take derivatives. It's coming in the next section. Before we get there, we need to just take a minute to talk about notation, all right? So right now, if I give you y as a function of x, then if you see f prime of x, that means I want you to take the derivative, right? So f prime of x means to us, take the limit as h goes to 0 of f of x plus h minus f of x all over h, okay? Now that's the same formula we were using last class. I'm just replacing the a with x, okay? But it's the same thing. So this is what that notation means. Now if I want you to take the derivative, I'm going to use this, right? F prime of x, but I could also use any of these. These are all notations that mean the same thing. Okay, so like if you see y prime, just y with a little prime mark on it, that means I want you to take the derivative of it. All right. If you see this dy dx, dy over dx, that means to you, take the derivative of the function, all right? Now, there's a reason why we have all these notations, okay? First of all, calculus was discovered by two people. I told you this in the beginning of class. Maybe, I don't know how deep I got into this. Isaac Newton and Gottfried Leibniz both developed calculus independently from one another around the same period in time. And it's debatable. I've actually heard recently that people are thinking that Gottfried may have copied Newton, but we're not getting into that. Leibniz used a different notation. I mean, you have to imagine if they were making calculus up out of nothing, then they're going to have different notations, right? Because there was no notation, no established notation for anything. So they had different notations. And so this dy dx is Leibniz, that's Leibniz's notation that he used, all right? And it actually turns out that sometimes Leibniz notation is better. It makes a little more sense. Later, you'll see this. And sometimes Newton's makes more sense. So we use them both. It's not like we just said, no, let's just do away with one of them. They're both useful, so we keep them. If you see df dx, that also means take the derivative of the function. If you see ddx in front of the function, then that's this right here saying, hey, take the derivative, all right? Take the derivative of that. Capital D in front of the function means take the derivative. Capital D with the subscript X means take the derivative. I know that that's annoying, but if you take Cal 3, if you ever get to Cal 3, if you have to take it, you'll understand why these notations are necessary, because later on, instead of like everything we do in Cal 1 and Cal 2 are all functions of a single variable, meaning every function we ever deal with is like f of x, right? You give me an x, it'll spit out some value. But when you get to Cal 3, you have functions that take more than one input in. So maybe they take 3 things in and then spit out, I don't know, some weird algebraic combination of those 3 things. So like you give me x, y, z, and then the output is x squared times y plus 3x times e to the z. I don't know, I'm just making that function up out of nowhere. That is a function of 3 variables, not 1. And so in Cal 3, we have to take derivatives also. Now it has different meaning, but if I'm going to ask you to take the derivative, I need to tell you what variable I'm asking you to do the derivative with respect to. It's important in Cal 3. So with this notation, this easily indicates what variable you're differentiating with respect to. So again, it's hard to explain because you're not there yet, but later on you'll see the value of having multiple notations for this. All right. All right, so these are the notations and Leibniz, right? Blah, blah, blah. Okay, so now some definitions. Differentiable functions. So, believe it or not every function is differentiable. Meaning you cannot take the derivative of every function. Some functions, the derivatives don't exist. I'll give you a quick example before we get too far into this. If I just graph right here, the absolute value function, that's f of x equals the absolute value of x. You can take the derivative of this function everywhere except 0. F prime of 0 does not exist, right? Because you have a corner there, right? I already talked about this. So not every function is differentiable everywhere, right? So this definition says a function f is said to be differentiable at a single point A if the derivative exists. Okay, so if I say, hey, is that function differentiable at 2? Then that means f prime of 2 needs to be a number, all right? But if you extend beyond that, you can talk about the differentiability of a function on an open interval. Meaning if the function is differentiable at every point inside a specific interval, then we will say that it exists, the derivative, the function is differentiable on that interval if the derivative exists for every point in the interval. So looking at this function over here, the derivative does not exist at 0, right? But how about on the interval from 0 to infinity? Is this function differentiable from 0 to infinity?
No,
Yeah.
because it's not differentiable at 0.
No, but I have a parenthesis at 0. Do you see that?
Oh,
I
yeah,
don't
yeah.
have-
So
I don't
it
have a
would,
bracket.
it wouldn't
It's going
count
to be
the other
that
side.
constant line again, but yeah.
It'll be constant, but yes, it's differentiable. The derivative exists everywhere over here, right? Same with to the left of 0. To the left of 0, I've got derivative. I can talk about slope of tangent line at all these points. So to be differentiable on an open interval just means that you are differentiable at every point inside. Okay, differentiability implies continuity. So remember continuity. If there's a few sections ago and y'all didn't like it, I told you I don't even like that section. Continuity is the idea of drawing a function without picking up your pencil, right? That's what continuity is. Can you draw the function and not pick up your pencil? Differentiability implies continuity. If a function is differentiable at a point A, then the function must be continuous there. If you don't have differentiability, well, hold on, let me just stop before I say this. If the function is differentiable at A, then it must be continuous. So differentiability implies continuity. If you're differentiable, then must be continuous. So it's impossible to talk about, hey, yeah, this function, the slope of the tangent line there is 2, but then tell me that the function is not continuous there. That's impossible. Differentiability forces continuity to happen. Now, students mess this up, okay? So I want to give you an example of something that I hope will help you understand how this sort of thing works. This is a logic idea. If you've never taken logic, which most of you haven't, I just want to see if you can understand this. This right there, that symbol is the implies symbol. Oh, implies. So differentiability implies continuity. So let me give you an example, a real world example I think will help you understand implications. So Texas implies US. Okay, so what I mean by that is, if I tell you that you physically live in the state of Texas, right? You're standing in the state of Texas. That implies you're standing in the United States, right? At least now, right? I mean, who knows? If Texas decides to go its own way, I doubt it. Okay, so if you're standing in Texas, then you're standing in the United States, right? Does that implication work the other way around? Can you, so suppose this is
No.
true, right? Can you just flip the order and say US implies Texas? So if you're standing in the United States, does that mean you're standing in Texas?
Not necessarily.
Not necessarily, right? So this is false. So when I say that differentiability implies continuity, that does not mean that continuity implies differentiability. This is not true. And the perfect example of that is that absolute value function again. Can you draw this without picking up your pencil?
Totally.
Yeah, but does that mean you're differentiable? No.
No.
No, in fact, there's a point right here where I'm not differentiable. But if I tell you you're differentiable, then you have to be continuous. All right. All right, let me see. All right, so the question becomes, when do functions fail to be differentiable? I've already given you one example, right? One place they fail is at any sort of corner. So if you have a corner or a cusp, you will definitely not be differentiable there. I'll show you what a cusp is in a second. If there is a jump in the graph, so if the graph breaks, you cannot be differentiable at that break. And if you have a vertical tangent line, you can't be differentiable there. So here's the first example. Right, corner. Can't be differentiable at this corner. And I illustrated this already. As you move, you know, the tangent line, the slope of the tangent line is constant, and all of a sudden, immediately, right? It's like going from hot to cold, right? Boom, you switch. And because of that rapid switch at 0, it's undefined. Get over there. Get over there. Stop. It won't let me. There we go. At the corner, it's undefined. Okay. Once you get past the corner, yeah, it's defined. So not differentiable at that corner. I don't think I do a cusp, so I'll just draw you a cusp. A cusp looks like a corner, but it goes like this instead. That's what a cusp looks like. So that would fail to be differentiable here too. And for the same reason, is you come in from the left, right? Your slope of your tangent line is positive. And then as soon as you get to this peak and you step over the peak, you immediately flip over to negative. And that rapid change makes it not differentiable. The next type is where you have a jump. And I think you can understand this, I hope, if I graph the derivative. So if you're coming in from the left, the derivative is positive, right? Positive, 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 positive. And then all of a sudden, right here, all of a sudden, it flips, and now it's something different, right? So this discontinuity, this jump, right, in the original graph causes the derivative to not exist there.
So question.
Yeah.
What if there was the same slope on both ends of the jump?
Then it would be differentiable. But then
Yeah.
you wouldn't have a break in the graph.
But it also wouldn't be continuous though. I'm
Oh,
saying
okay,
like
I see
if
what
you
you're
have
saying.
a slope like this and then it breaks and then there's
Yeah,
another
okay,
one.
I see. I thought you meant put them together. So you're saying, hold on, you're saying, what if we had that happening?
Yeah, like if it continued at the same slope, just at the break, because that would be continuous.
It would not be continuous, and therefore it would not be differentiable.
So
Okay.
if a function isn't continuous, its derivative can't be continuous either.
No, if a function is not continuous at a point, then it cannot be differentiable there.
Okay.
Let's go back to the thing that we talked about a second ago. If you're from Texas, right, that implies that you are a US citizen, right?
Yeah.
That does not work the other way around, right? US does not mean that you are from Texas. However, there is something that is true. If you're not from the US, that implies you are not from Texas.
Yeah.
Now, it's not the same as this. So taking this and flipping it over is not true. But if you flip it over and negate both statements, it is true. This is known in logic as the contrapositive. Again, if you haven't taken logic, don't worry about it. This isn't a logic class. But if you're given an if-then statement, an implication, the contrapositive is equivalent. Have any of y'all ever heard of truth tables? Logic? No.
Like in coding?
There are truth tables, yeah, and computer science uses a lot of logic. The truth tables for these two statements are equivalent, which means that they are equivalent. Again, if you've never heard that, don't worry about it. But the reason I'm mentioning it is because we're saying that differentiability forces continuity to happen. But the contrapositive of this is if you're not continuous, that means that you are not differentiable. And therefore, to answer your question, Hunter, even if the slopes on both sides were equal, if you have the jump, if you have the break, you don't have continuity. And as soon as you don't have continuity, you lose the differentiability.
Okay.
Okay. Okay.
Would that just be, if you were to graph it, would that basically just be a hole at the point? Because your line would continue straight.
Even if you put a hole there, right? Even if we just did like that's a hole and continued like that.
I'm talking about on the graph of the on the graph of the derivative, would that just appear as a hole?
Yes.
Okay.
Yes, it would be a hole in the graph of the derivative. The derivative would still go through. So the derivative would look like this, whatever it is.
Yeah. Okay.
Yeah.
I was just wondering because that
Yep.
seemed like an oddball.
Yep. All right, good questions. All right, the last type of place you cannot have a derivative exist is where you have a vertical tangent line. Now, there aren't a lot of functions that behave this way, but some do. And so watch the tangent line here and notice the value of the tangent line. It's positive, right? Because we're increasing there. But as we start to get here, look what's happening to the tangent line. It's starting to want to, oh crap. It's starting to want to, damn it. See how it's getting steeper? I'm getting closer. Look at it, it's at 33 now, getting closer. I'm at 154. Getting closer. Look at the slope of this tangent line. It's 718. If I get closer and closer, that number gets bigger and bigger. So like theoretically, if I were ever to get right to the middle of there, the slope of the tangent line should just for an instant go vertical, right? And what is the slope of a vertical line? Undefined. Okay, vertical lines have undefined slopes. And so since the derivative is the slope of the tangent line, if the slope of the line is undefined, then so is the derivative.
Would that make a vertical asymptote?
No, because this function doesn't have a vertical asymptote, right? Like this function does not have vertical, or are you talking about the derivative?
Yeah, the derivative on the derivative, would that give us a vertical asymptote right there?
Yeah, let's look at it. Let's look at the derivative. Watch, here it is. I'm graphing it. And then now it's getting steeper and steeper. And so, whoa. And then when I get to the other side, it's real steep over here also. So look, the derivative has a vertical asymptote at 0. I'm sorry, I thought you were talking about the original function.
Sorry, I'm not clear on this sometimes.
No, that's good. That's good that you're seeing that.
So is that because does that have something to do with the vertical line test, like the original function, or is that just something completely different?
No, because this is still a function. If you draw a vertical line, it will hit this graph, okay? Like if I draw a vertical line right through the y-axis, it will hit that graph at only one point. Okay, the problem is, what is the slope of a vertical line? So if I give you a vertical line, ask you what's the slope, it's undefined.
Being divided by 0.
Yeah, it's rise over run, right? Rise over run. And so if you take 2 arbitrary points on that line and go from one to the other, the rise is a number, right? But then the run is your left to right, and your run would be 0. And division by 0 is undefined. Now this is different.
Okay, I never knew that.
Yeah, this is different than 0 over 0 in a limit. This is totally different. This is a number divided by 0, and that is just undefined. Yeah, so I don't know, in college algebra, you talk about lines and you say, okay, if the line is pitched like this, the slope is positive. If the line is pitched like this, then the slope is negative. If the line is flat like this, the slope is 0. But if the line is vertical, the slope is undefined. Okay. How are we doing? 211. 211. 211 is a band, right? Has anyone ever heard of 211?
Isn't that 311?
Is it 311? Is it 311 or 211? 311? Who cares? Oh, okay. So last thing here. So mathematicians are weird. Okay. Once we have theorems, we always start to like go down these weird, like dark alleys, right? And start to ask these really like crazy questions. So we know that differentiability, right? There's a theorem that says differentiability implies that you're continuous, right? Right, we know that. Differentiability. So mathematicians ask this question: is there a function that's continuous, but nowhere differentiable? So is there a function that you can draw without picking up your pencil, but any point you ever go to, you can't take the derivative? So before you think about this incorrectly, let's go back to the absolute value function. That is a continuous function, right? It is only it only fails to be differentiable at one point, right? Everywhere else it's differentiable. There's one point that it's not differentiable. Mathematicians asked, is there a continuous function, a function I can draw without picking up my pencil, where no matter where you go, you can't take the derivative?
That doesn't seem feasible.
It doesn't seem like it, right? It doesn't seem like it would be possible to draw a function without picking up your pencil, but never be able to take the derivative, right? Well, there is one.
Wait, I think I know what it might be. Would it just
I'll
be a
give you
vertical line?
That wouldn't be a function.
Right, I forgot about that.
Yeah, that'd fail to be a function. No, nobody's going to get this. I mean, nobody's going to get it. All right. I mean, unless you've heard of it before. Okay. It says it right here, so it's kind of giving it away. It's called the Weierstrass function. Okay. And here's what it is. This is the computer trying to graph it. Okay. It's hard to graph because it's a crazy ass function. So what it is, it almost looks like a sine function or a cosine function, right? Kind of the periodic up and down. But if we zoom in, let me kind of zoom in on one of these things. So it kind of looks, that looks like you could take the derivative, right? Like in here.
Yeah, those
that's
little,
nice and smooth,
yeah, before it
isn't it?
switches.
But it's not, okay? Because if I zoom in more, hold on, that's just, if I zoom in more, yeah, it's really hard to see it here. What it is, it's a function that does, there's no way to draw it with a computer because the computer will fail to do it correctly because the computer has limitations. Imagine a function that does this. It's a function that goes like this and draws jagged edges like this, right? Now at each of these corners, it is not differentiable. Do y'all agree with that? Now, what if I told you that when you zoom in on this, like magnify it and look at it, this little piece actually looks like this. Think of it like a serrated edge of a blade, right? So this is a serrated edge. And then when you zoom in on one of those serrations, that is also serrated. And then when you zoom in on one of those serrations, it's also serrated.
So it's just constantly doing those little jagged things.
And
Would
you
this
can
qualify
zoom
as
in
like a
far as you
fractal,
want.
sir?
What's that?
Would this like qualify as like a fractal? Without
It's kind of in this almost a fractal because it's the function is something you've never seen before. It's actually a series, an infinite series of trigonometric functions. I'll show you the function. I don't think I put it in here. Yeah, I didn't put it in here, but we'll just look it up on I think I spelled that wrong, but we can bring it up. Leave the page. Here we go. So this is I think this is a better picture of it. There we go. Okay, so this is the actual Weierstrass. Can y'all kind of see that? I know we don't really want to trust Wikipedia, but I've been to this before on Wikipedia, so we can trust this. So it's like you look at it, it's a bunch of jagged edges, and then when you zoom in on one little edge, you get a bunch of more jagged edges, and you can just do this forever. So here's the function right here. This is it. So for those of you who don't know what this is a summation, which means we're just going to add up a bunch of shit. So what we do is we start with n being 0, and I replace all my n's with 0. So a to the 0 cosine of b to the 0 times pi x. Okay, that's really just cosine of pi x, because anything to the 0 is 1. That's when n was 0, right? Then I add to that another function. Now I let n be 1. So if n is 1, we get a to the first power cosine of b to the first power pi x. And then we let n be 2, a squared cosine of b squared times pi x. So each of these are cosine functions. And so we're adding up how many of them?
An infinite, right?
An infinite number of them.
That number on top means how many times to do it, right?
That tells you where to stop. And
Okay.
that means don't stop. Now, it's a whole different exercise to prove to you that this is continuous and differentiable. I'm sorry, continuous and nowhere differentiable. It's a whole different exercise. And it's nothing I can do in this class because it requires that you understand that you've learned like how to prove theorems and the precise definitions of limits. And you remember in the beginning of this class, we said we were going to not deal with something, the idea of close and near, remember? We said we're going to wave our hands at it, and that mathematicians have a precise way of doing it. And so when we waved our hands at that, we are definitely nowhere even close to me for me being able to show you that that's continuous and not differentiable. Okay, so but it's out there. I just wanted to share that with you.
Quick
not in the
question.
textbook. Mhm.
What dictates the value of a and b in this function?
They just have to be, there are just some conditions on them. So the conditions are that a is between 0 and 1 and b is a positive integer, and that the product of the two is greater than this number. So
Okay,
as long as that's true, then this will be a.
So does that mean that for each time that's done, there's also every feasible a and b that matches those requirements?
There's an infinite
we get-
number of a and b's that you could use here.
Yeah.
Yeah, there's an infinite number of them.
Oh,
There's
that
an
okay.
infinite number of functions that would satisfy this.
Oh, that's horrific.
Yeah, this is kind of cool. This is an animation. You know how I showed you in the beginning, it was just one cosine function. And then we added a second one and then a third one. This animation shows you, look, when it starts at the beginning, it's going to look like just a cosine. There's adding a few of them, and then just keep on adding a bunch more. And that's what it starts to turn into. The further out you go, the crazier the graph starts to get. And that's where you start to get all the jagged edges. Okay, let's get out of here. All right, so now that we have talked about where a function fails to be differentiable, I've got good news and bad news. I don't know how you want to look at this. If what we have established today is that we can start with f of x, right? We start here. We can do the derivative, right? Take the derivative of this and come up with a new function, right? Right, this new derivative, but it's just a function we could graph it, right? If that derivative is a function, then what is stopping me from taking the derivative of that function?
I knew you were going to say that.
Yeah, this is gonna be like an infinite series of taking a derivative.
Why not do the derivative again? That would be the derivative twice, wouldn't it? And so that would be what we call our second derivative, but that should spit out a new function. And what's stopping us from taking derivative of that again, right? So we need some notation, all right, and some language for this. And then we will talk about what it means because they actually have meaning. Like the first derivative means something, the second derivative means something else, and the third derivative means something else. So we'll get to that, but let's just get the notation out of the way first. These are called higher order derivatives. Okay, so f prime of x is what we call the first derivative. Okay, if you put two little prime marks there, well, then that's the second derivative. That means you're going to take the derivative of the derivative, called the second derivative. If you put three prime marks there, well, then that's the third derivative. This makes perfect sense, right? That's the derivative of the derivative, right? You're doing original function, taking derivative, and then derivative of that. So you've done the derivative 3 times. Now it starts to get ridiculous because you don't want to put like, 17 prime marks, right? To represent the 17th derivative. So what we start to do is we start to move away from the primes and we start to put a number there. Now, be careful, because there is a huge difference in notation. If I have a function and I write f4 of x, let's do it this way, versus f parenthesis 4 of x, these mean two completely different things. The first one means take the function and raise it to the 4th power. For example, let's say we started with the function f of x equals sine of x, a good old trig function from pre-cal. Then if I asked you to do this, then what you're going to do is take that sine function and raise it to the 4th power, which we have other notation for that. We like to write it this way instead. But that's what this notation means, okay? If you just put a number there and you do not put parentheses around it, then you're talking about raising things to powers. If we put a parenthesis there, then what this means is that you're going to get the 4th derivative. That means you're going to take the derivative once and get the first derivative, then take it again and get the second, and then take it again and get the third, and then take it again and get the 4th derivative. Big difference.
So hypothetically, as you continue with a given function, will you eventually hit a point where you can't keep taking the derivative?
What do you think? Everyone think about that. So Hunter's asking, if we start with a function and we take its derivative, is it going to get nicer? Is it going to get uglier? And then if we take the derivative again, are we going to eventually get to a point where we stop, like we terminate? So let's go to the polynomial idea. If we start with x cubed, right? We took the derivative that first time and I told you were going to get what?
X
X
squared.
squared.
Something with x squared, right? And then you take derivative again, and then you go from x squared down to what?
X to the first.
X.
X to the first, or linear, right? What would happen if you did the derivative again?
When you get x to the power of 0,
Variables.
X to the 0, which is just a number, isn't it?
it's just 1.
Right? Just a constant. And then what do you think happens if you take derivative of a constant? Don't answer that. Hold on.
Death.
Let's imagine you have a function that is constant. And I'm asking you for its derivative, which is me asking you at what rate is it changing? If it's constant, then what's the rate of change?
There is no rate
Zero.
of change.
There is no rate of change,
Consistent.
right?
Yeah.
It's 0. Then that's what would happen. And we're going to have formal rules for this next class. But start with x cubed, take the derivative once, you go to x squared, take it again, you go to x, take it again, you go to a constant, take it again, the constant goes to 0. So that makes it look like if you do the derivative enough times, it actually goes down to 0 eventually. That's what it looks like, right? I agree with that only for polynomials. That's the bad news.
So that only works with polynomials?
Yeah. In general, it just depends. Sometimes it gets nice. Sometimes the derivative gets cleaner and maybe it'll go to 0. Sometimes it gets so complicated that you can't go past the second or third derivative because it just becomes so massively difficult. And then sometimes it actually becomes cyclical, which means that you'll take the derivative, or you'll have a function, you'll take its derivative, you'll get something. And then when you take derivative again, you get back the original one. And then you get caught in this cycle, this like loop. It just depends.
That's really cool, actually.
Yeah.
Is that like that whole
I'll spoil it
antiderivative?
for you. Sine and cosine do that. Sine and cosine, those functions, when you take their derivatives, they start to cycle back and forth between each other. Okay. Now, this is this notation right here that I'm showing you, right? This notation for first, second, third derivative, fourth derivative. This is all the notation we use when we're using Newton's notation. Leibniz had his own notation. So here's the way Leibniz notated first, second, third, fourth, fifth derivative. And I have to unfortunately point something out here too, so that you're careful. So the first derivative we know is dy dx. Okay, I told you that already. But here's how he notated the second derivative. He put a d, then of 2, then y, and then he put d, and then x, and then 2. Notice how these 2's are offset from one another. See how they're not lined up? Like the 2 on top is not above the 2 on the bottom. The reason Leibniz used that notation for the second derivative is because he didn't want us thinking that if he had done it this way, he was afraid that you might think that we mean take the derivative and square it. See, this right here is the first derivative squared. That is not the same as the second derivative. The second derivative is take the derivative, then take the derivative again. The first derivative squared is just take the derivative and then square that answer. So he didn't want this happening, so he offset these 2's. And you can see it, same here. He offset the 3's, offset the 4's, offset the 5's. Okay, here we go. How are we doing? 228. So position, instantaneous velocity, and acceleration. So coming into today, I had already told you, okay, I had already told you that if a function gave you position versus time, in other words, if you graph it, if this is time and this is position or distance, then the derivative from last class would give us the instant velocity, the speed. The first derivative of a position function gives you the speed of that object at a specific point in time. Do y'all feel like I already established that for you last time? Yes? Okay,
Yeah.
now what does the second derivative give you? I'm going to try and see if I can squeeze it out of you. So yeah, I really like this to talk about this. So let me try and force it to happen here. Let's say that this is, hold on, this is time, and let's measure time in seconds just for this example. And let's say this is your distance, and let's say this is measured in meters. Okay. So I'm going to draw you a position function, just a crazy, just abstract function. There it is. Now, if I go to some point X, and I go here, f prime of X is going to be some number, right? And what did we say last class the units of this number would be? Does anyone remember what the units of this number would be?
Meters per
Meters per
second.
second.
Meters per second. Why? Because slope is a rise over run, right? And if your rise is in meters and your run is in seconds, then meters over seconds, meters per second is your unit. So this would be in meters. I'm just going to put m over s, right? That's the first derivative. Now, that's a speed, right? That's a speed or velocity. For those of you who've taken physics, I understand that speed and velocity are not the same thing. But at this level right now, we're just going to treat it like it's the same, okay? Now, imagine now we take this function and we graph it, because we can graph the derivative, right? It has its own graph. So now I'm going to graph the derivative. Here it is. So let's say that that's the derivative. The x-axis is still time in seconds. But what's the y-axis? It's not distance anymore, because the derivative doesn't tell us distance. It tells us what?
It's your speed.
It's your
Meters
speed,
per second.
right? So this is your speed, right? Which is measured in meters per second. So if I come in here now and take the derivative at some arbitrary point x and look at the slope of this line, this second derivative at that x is going to be some number, isn't it?
Yeah.
To give
What are
you
the
your
units?
instantaneous acceleration.
What are the units? This
Meters per
over this, right? which is
Meters per second squared.
meters per second, which if you've taken any physics classes, know that that's meters per second squared, which is what we use to measure acceleration. So what is this all about? Why am I saying all this? What do you need to take away from this? If you have a function that gives you the position of an object, the first derivative gives you the instantaneous velocity. And the second derivative gives you the acceleration. Okay, start with position function, take the derivative once, you'll get the velocity function, take the derivative again, you get the position function. Has anyone, or do any of y'all remember seeing this formula in college algebra, or maybe in a physics class? D of t, it may have been some variation of this, equals -16 t squared plus v naught t plus d naught, something like that. Anyone remember seeing something like that ever? No? Okay, if you don't worry about it. This is actually the equation or the function that gives you the position of an object if you drop it on Earth. Okay, so t is time. The function measures how high this object will be. Let's put this on hold. We'll do this later. Hold. We'll do it when I'll give you the shortcut rules and then we'll come back to this. All right. So I don't think we have much time to do anything else. Let me see. Yeah, so we're ready for the basic differentiation formulas. Yeah, I do have time for one thing. Did I talk to y'all about Pascal's triangle?
No.
No? Okay, we have enough time for me to do that. It'll become useful for next class. We are done with this section though. When you do the homework, you're probably going to look at it and be like, what? He didn't really talk about that. Read the questions, all right? Try and understand what they're asking, because this section is really about, do you understand concepts? It's not as mechanical as the previous sections. So think about what you're being asked. Okay, so clear your minds for a second. This is something that is just an algebra thing that will help us when we get to the next section. So let's say we have a binomial, x plus y. Well, you know what? Let's go x plus h. Let's do x plus h. I want to know what that would be if I raise it to the 0th power. So what's anything raised to the 0?
1.
1. So this is equal to 1. Now I'm going to write the 1 out here. Just trust me. Just do that for a moment. Now, what would x plus h to the first power be? So anything to the first power would be
Just be x plus h.
Okay, I'm going to write it this way: x plus h. I kind of centered it on the 1. You see that? I put the plus right below the 1. Okay, now I'm going to do x plus h squared. So if I did x plus h squared, I'd have to do that up here. X plus h times x plus h. I'd FOIL out. And I think you've probably done this enough with a plus h in your homework that you would be comfortable with the idea that this would give you x squared plus 2xh plus h squared. Yeah, collect like terms, yes? Now, what about x plus h cubed? That's kind of like the quiz problem, isn't it? Didn't you have to do that, a plus h cubed in the quiz? Okay, so that means you have to do x plus h times x plus h times x plus h 3 times, right? And do all them expanding out. What does that turn into? X cubed plus 3x squared h plus 3xh squared plus h cubed. That's what it turns into. You trust me? All right.
Looks good to me.
What about the next one? Anybody know what x plus h to the 4th is? Come on, you should know this now. I'm kidding that you should know this. I mean, it's obvious, right? X plus h to the fourth is x to the fourth plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth.
Sure.
Yeah. So what I'm doing right now is I'm just showing off. I'm doing all this mentally, and I'm just a freaking machine, man. Look at me. Look at me. It's impressive, isn't it? That I can do all these mathematical computations in my head. Pretty proud of myself. Make sure I don't screw it up. I'm screwing it up. There we go. That's right. That's what it is. All right. So how many of you think I actually know this like out of my head? I don't know this out of my head. Okay. There's a pattern here. Okay. And so let's establish the pattern. Let's start the pattern by noticing just the x's first. Okay. So I think I'm going to start with this one right here. All right. This one was originally raised to the third power, right? Okay. Just look at the x's in the answer. Where do we start? X cubed, right?
Yeah, x cubed,
The next x term is
x squared,
squared. Next one.
x,
Next one.
It-
Gone, right?
gone, yeah.
So you could say that like as you move from left to right, the x started out as x cubed and then went down to x squared, then down to x and then gone. Yes? Does it do that in all of these? When you go x to the, this to the fourth, x to the fourth, x cubed, x squared, x gone, right? This
Yeah.
to the fifth, x to the fifth, x to the fourth, x to the third, x squared, x gone. So the pattern is that as you move from left to right, the x's start out with the power and then they vanish away, one power at a time. What about the h's?
They're doing the same thing, but backwards.
Backwards. So you could look at it like from right to left, they're vanishing, or you could say from left to right, they're appearing, right? It's like you have no h's. Oh, there's an h. Oh, there's an h squared. There's an h cubed. No h's. Oh, there's an h squared, h cubed, h to the fourth. No h squared. Make sense?
So what did you do for those constants then?
Yeah, that's the question, where the constants come from. So let's do the next one, and I'll get to the constants. Let's just see if we can take care of the x's first. Or sorry, the variables. So I know that this one should be x to what power?
The sixth.
6?
6 plus, there's going to be some number here, but I'm not sure what it is yet. Then it'll be x to the
Fifth.
5th?
and then an h, right? An h is going to appear. Then some number, what power on x?
X to the fourth.
4
H squared.
squared. And I'm going to keep doing this until all the x's vanish and I end with h to the 6th. So I'm going to have some constant and then x to the third, h to the third also. And then plus some constant x squared h to the fourth. I'm running out of room. Plus some constant x h to the fifth. And then plus the last one will just be h to the 6th. Notice on the edges, the coefficients on all the edges are ones, aren't they?
Yeah.
So now the big question, what are the numbers, right? What are these numbers? And
With
this
the-
is where, the what?
Would the first and the last numbers be 6?
They would be 6. You can kind of see it in the pattern here, 2, 3, 4, 5, 6, right? Y'all see that pattern?
Yeah.
Yeah.
And the other way, it's like 2, 3, 4, 5, 6. The harder part's the middle, but
Yeah. I don't know
there
what's
is a
going on there.
pattern. There is a pattern. And to show you the pattern, I'm out of time. To show you the pattern, I want to just look at all the numbers, the coefficients only. 1, 1, 1, 2, 1, 1. Oh, if you need to go, you can go. 3, 3, 1, 1, 4. This will be on video if you have to go. So 1, 5. Okay, we have them all, right? I'm going to write them down like this: 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. Okay. I just put them all here, but there is a pattern. Here's the pattern. The numbers on the edges are always ones, always. Pick any number in this triangle, and it is the sum of the two above it. So this 6 is the sum of those two. That 2 is the sum of those two. This 5 is the sum of those two. This 15 is the sum of those two. This 20 is the sum of those two. This 15 is sum of those two. That works for every number. So what would this number here be? The sum of what two numbers?
5 and 10.
5 and 1. 5 and 1, these two.
Oh,
Which would be
right, yeah,
6.
just looking at the wrong one.
And then what would this number be?
That'd be 5 and 10.
15.
5 and 10, 15. Okay, now careful because it's hard to see this. This one should be the sum of these two, right?
Yeah.
So 20. And then this one should be the sum of those two, 15. This one should be the sum of those two, 6. And then the last one's 1. This right here is known as Pascal's triangle, named after a mathematician, last name Pascal, but Pascal was not the one who discovered it. So I don't know why he gets credit for it, but he does. All right. So your homework for tonight is just to turn in that quiz, right, by 3 o'clock tomorrow, and then do the homework for 2.2, which should be pretty clear. Yeah, it's a lot of work. See how it goes. I'm sure you'll have questions. Okay. I think we're done. So have a good week. We have an exam in what, about a week and a half? Yeah, October 5. But we have a lot to do still. Have a great weekend.
You too, sir. Thank you.
Thank you. You too.
I wanted to quickly ask for homework 2.1. We didn't have to do the last two on that thing, right?
Yeah, sorry I didn't get back to you. Yeah, I scratched them out in the video. I think I said that at the end of class not to do those.
Okay, I just wanted to make sure because I made sure to do like all of the ones before that one, and then I wasn't sure if we needed to do the last two.
Yep. Okay.
Sorry, I had a question. I haven't had time to go to your office hours just because of work. Would I be able to go through one question for you on 2.1?
Which one? 2.1?
Yes, 2.1.
Yeah. I actually do have time today. Did you all want me to do a breakout room or just leave the session open? Ethan, you still want me to do that or what?
Yeah, I think I saw where I made a mistake, and my group got
Okay.
a different answer than me, but I think I saw where I made a mistake. Small algebra mistake.
All right, which one, Ricardo?
So on 2.1, question 26, it's just I used both methods to try to get the answer, kind of fact check it,
Mhm.
and I got similar. It's the answer was 6a squared, but for the other method, I got 6a squared plus 1.
Second one is right.
The 6a squared plus 1.
Yeah,
Would I be able to share my screen with you?
yeah, absolutely. Does anyone have a quick question, or because I don't want to make everyone wait if there's just something quick? No? Okay. All right, so let me stop sharing and then let me make you a co-host. All right, I think you should have control.
You can see it, sir?
Yes.
Okay, so I think so this is the first method using limit as x approaches a. I wanted to know this part right here. Is that a 1?
Okay, let me look here. So you did difference of cubes formula. And then, okay, so what happened? Oh, I see the problem. Yeah, it is a 1. You canceled those x minus a's. You cannot cancel them because you have a plus sign in front of that x plus a.
Right. Yeah.
So you could cancel all the x plus a's and it would turn into a 1, right?
Mhm.
Let me do this. Let me grab this. Stop sharing yours. And then I'll share mine. Okay, so right here, think of it this way. If you had 2 times 3 times 5 plus 3 over 3, okay?
See anything
All right.
else?
You canceled the 3's like that. Oh, wait, I'm not sharing. I'm sorry.
Yeah.
Sorry. Okay, so let's just take that idea, right? You have 2 times something plus, these are the same, right? Oh, wait, was that a plus or a minus? Ooh, that might be why. But okay, you're gonna have to share again. What I'm getting at is, look, at this, you cannot cancel these. You cannot cancel these. Because of this plus sign, you would have to have an x minus a over here also.
Right.
Then you could cancel it from all. It's like this 3 right here. What you did is like that, which you can't do. You could do all the 3's. So you share your screen again because there's something wrong
Sure.
in the algebra there.
I think I see it.
Yeah, okay.
Yeah, up above it was an x minus a. I wrote x.
Oh,
plus
yeah.
a.
Yeah, okay. So then they would all cancel and it would become a 1, right? Plus 1.
Right.
And so that should give you the 6a squared plus 1.
Okay. Because I noticed you did. I got this. I didn't know how to do this. There was this trick that you did on one of your homework solutions, and I tried it where I grouped the 2x cubed minus 2a cubed, and then you said that you have to also cancel this one over here as well. That was that was the only part that I kind of wanted to focus on. Well, that cancels because it was separated up here, wasn't it?
Are you still referring to that same step where you
Which
canceled
one?
or?
On step number 5 right here.
Yeah,
Yes, so that x, because that should have been a
yeah,
minus.
that's a minus. You're
Right.
still questioning why it cancels?
Yeah, it cancels because up here, or originally, it looked like this originally,
Yeah.
right?
Mhm,
So it has to cancel because I moved things around, and
mhm.
that x minus a is not by itself, but it's up here as well.
Okay, but see the plus sign between them?
Yes, I
That
do.
plus
This one
sign?
right there.
Yeah.
Yeah.
Okay, so that means you have 2 terms. Everything to the left of that plus sign, everything to the right of that plus sign, right?
Right. Yes.
Both of those terms have x minus a, don't they?
Yes. Mhm.
So you can factor out, on top, you could factor an x minus a out of both terms.
Oh, I
So-
see.
so-
Okay.
Put it, yeah, just write it down. Put x minus a out front,
Right. Let's see. So in front of which one?
just in front, just out in front of, just top left, just anywhere you want. No, go below that. Like start a new line.
Okay. So
Yeah, x minus a, put it in parentheses. No, put the x minus a in parentheses. Okay, now put a bracket. Okay, now you took an x minus a out of the first term, so you're left with the 2, right?
2.
And everything in the 3 terms in that parenthesis, put them there next to the 2.
So the x squared.
X squared plus xa plus a squared. Okay, close parentheses. Right? Plus, now that plus sign, now you took the x minus a out of that last piece completely, right? So that's 1. There you go. Close the bracket.
That
Now
okay.
put all of that over x minus a.
Right, and then
There you go. Does that make more sense?
yes, it does. Okay. I was trying to figure that out, whether what I got wrong and right. I mean, I could see why this one, that was a 1, but I was trying to see that over here. I guess that it's a hidden 1, I suppose.
Well, it's a 1 because you factored it out. So if
Right,
you
right.
distributed it back through, it would have to show up. If you don't put the plus 1 there, then it's not going to show up,
Right.
right?
Yeah, it makes more sense looking at it like this with the brackets and stuff. Okay.
Yeah, the brackets could be parentheses. That was just to kind of force you to see like the x minus a is coming out of everything. So yeah.
Okay. That makes sense, sir. Thank you.
Okay,
Appreciate
cool. Good. Yep. Anything else?
it.
All
Pretty
right.
good. I'm gonna get going, sir.
Okay. Do you want me to leave the session open or are you good?
I'm good.
You're good? Okay. Anna Marie, Maddie, y'all are good?
Yes, sir.
Okay.
Yeah.
Have a great weekend, everyone.
You too.
You too, sir.
Bye.
Appreciate a good one.
Thank you.
Take care. Bye-bye.